In this lecture, I want to talk about induction or inductive reasoning and the Grue paradox. So recall that deductive logic classifies arguments as valid or not, whereas inductive logic measures the inductive strength of argument. In this lecture, we're going to say a little bit more about inductive logic or inductive reasoning. Now, there are in fact two main types of inductive reasoning. There's enumerative induction, so this is something of the form, given that all observed f's are g's, you infer that in fact all f's are g's, or at least that the next f that you see is a g. Or another type of inductive reasoning is the inference to the best explanation. So you see this often in detective novels. So for example, Sherlock Holmes might infer the best explanation for some evidence, for example, footprints, the absence of a barking dog, and the broken window, that the butler wears size 10 shoes, is known to the dog, broke the window to make it look like a burglary. In this lecture, we're going to focus on enumerative induction. So these are going to be inferences of the form, all observed x's have been y's, so therefore the next observed x will be a y. And in fact, we're going to consider a more general form of this because it's not often the case that every single observed x has to be a y for you to infer that the next x you see will be a y. Often it's enough that most of the x's or a large proportion of the x's have been y's for you to infer that the next x will in fact be a y. So you might say something like 99% of observed x's have been y's, so therefore the next observed x will be a y. Now of course, the second argument here, when only 99% of the observed x's have been y's, and then you conclude that the next x will be a y, this is less strong. This is not as strong as the first argument here, in which all observed x's have been y's. But this is a strong argument. So we might introduce a rule to capture this type of reasoning. We'll call this rule S. So suppose that n% of observed x's have been y's. Then you want to infer the next observed x will be a y. Now remember, with inductive logic or inductively strong arguments, we need a way of measuring the strength of this argument. So a natural thought is that the strength of this argument is just going to be n out of 100. So if 70% of observed x's have been y's, then you infer that the next x will be a y. The strength of that argument is going to be 0.7. So the higher the percentage of observed x's that are y's, the stronger the inference that the next observed x will be a y. So this is a very natural rule, and this seems to capture the type of inferences we draw when we make these types of enumerative inductive inferences. However, there are some limitations to this rule. So first of all, forget about these first premises right here. Both of these two arguments say the same thing. 90% of the observed emeralds have been green, so therefore the next emerald to be observed will be green. And the second argument here, 90% of observed emeralds have been green, the next emerald to be observed will be green. According to rule S, both of these arguments get assigned probability or inductive probability 0.9. So they're equally strong. But of course, this first argument, we're assuming that you've only observed 10 emeralds. And out of those 10 emeralds, 9 of them have been green, so you conclude that the next emerald to be observed will be green. Compare that to a situation in which you've observed 1 million emeralds, and 90% of those emeralds have been observed to be green. So therefore, the next emerald observed will be green. So the background information, or the reference class, the set of objects where you're drawing your observation, is very important to how you apply this rule S. Now we can illustrate this further with another example. Consider the following inference. every person who has taken drug X has exhibited no adverse side reaction. So therefore, the next person to take drug X will have no adverse side reaction. This is a very strong argument. After all, we're saying that every person who has taken this drug exhibited no adverse side reaction. So that means 100% of the people we have observed taking this drug X have exhibited no adverse side reactions. So therefore, the next person to take drug X will have no adverse side reaction. So according to Rule S, we should assign inductive strength 1 to this argument. So it's the strongest argument that one can give. But of course, the strength of this argument is going to depend on another piece of information. Namely, who did you test this drug on? Consider a situation in which drug X has been administered to persons between the age of 20 and 25 who are generally in good health, versus a situation in which drug X has been administered to persons of all ages and varying degrees of health. So obviously, in the second case here, when you administer the drug to people in all different ages and all different levels of health, that would make this argument much stronger than in the first case. There's another limitation to Rule S, and this has to do with something known as the problem of projecting regularities. So the key idea of an inductively strong argument, at least when we're doing enumerative induction, is that they project an observed regularity into the future. That's what's happening in this example right here. There's a regularity, namely when you take drug X, something you've observed is that there are no adverse side reactions. That observation, that regularity is then projected into the future, and you say, well then in the future, a person taking drug X, if everything else is similar, all things the same, kept the same, that person will not have any adverse side reaction. So that's the idea of enumerative induction, is that you're projecting an observed regularity into the future. But this leads to a puzzle and to a problem. So first of all, consider the following two arguments. 100% of observed samples of pure water have had a freezing point at 32 degrees Fahrenheit. So therefore, the next observed sample of pure water will have a freezing point of 32 degrees Fahrenheit. The regularity we observed is the degree at which water froze, assuming that all things are normal, that nature behaves uniformly, then in the future you can expect water to freeze at the same temperature, at 32 degrees. Suppose also that 100% of observed economic depressions have occurred at the same time as large sunspots. So there's some solar flare, some sunspot that you see, and it just happened to coincide always 100% of the time with economic depression. So therefore, that is also a regularity. This is a regularity that was observed in nature. But somehow we think that we shouldn't project this regularity into the future. Because this regularity this seems to be an accidental correlation rather than some regularity that we want to project, that we think ought to be projected into the future. So this problem of which regularities should be projected into the future has led to a very interesting and difficult paradox known as the Grue paradox. So let me introduce the property of being Grue. So a certain thing X is said to be Grue at a certain time t, if and only if X is green at t and t is before the year 2100. Or X is blue at t and t is during or after the year 2100. So the idea is we're on our timeline, so currently it is 2020, and we're looking at objects X, and we see that an object X is green, and so 2020 is before the year 2100, and so therefore that object is said to be Grue. But once you hit the year 2100 and you start observing objects, Once you see that object is blue, if the time is after 2100, then we will say that object is Grue. So Grue is a disjunctive property. You're green up to the year 2100, or you're blue after the year 2100, or 2100 during or after the year 2100. So now consider the following two inferences. 100% of the times that emeralds have been observed, they have been green. So therefore, the next time an emerald is observed, it will be green. This is a very strong inference. It is correct. 100% of the time that we've looked at emeralds, they have been green. So it's very natural. I'm going to assume that the next time I look at an emerald, that emerald will be green. So I should assign inductive strength 1 to this argument. Now consider the following argument. 100% of the times that emeralds have been observed, they have been Grue. So therefore, the next time an emerald is observed, it will be Grue. The inductive strength of this argument is also 1. But the question really is this a sound argument? Have 100% of the times that we've observed emeralds, have they been Grue? Well, in fact, they have. Every emerald I've looked at, it's before the year 2100. Every emerald I looked at has been green. And if you're green before the year 2100, then by definition, we've introduced this new property of being Grue. You are in fact Grue. So if you're green before the year 2100, then you have the property of being Grue. So this first argument, we all agree, is an inductively strong argument. If we agree that this first argument is inductively strong, then we must agree that the second argument is inductively strong. But that seems absurd. It surely isn't the case that emeralds are Grue. After all, Grue is this made-up, very odd property. So how can I prove or show or infer that all emeralds, or the next emerald I'm going to observe, is in fact going to be Grue? Now, one immediate objection or reaction to the Grue paradox is just to say, well, isn't green simpler than Grue? So green as a property is somehow a natural property, whereas Grue is this weird disjunctive made-up property that you made up to make this philosophical point. Well, if you think that way, then you can let's introduce a new property. Let's call it bleen. So a certain thing X is said to be bleen at a certain time t if X is blue at t and t is before the year 2100, and X is green at t and t is during or after the year 2100. So now we have green, Grue, and bleen. So in a language in which you speak Grue and bleen, the property of being green is in fact one of these weird disjunctive properties. So an object X is said to be green at a certain time t if X is Grue at t and t is before the year 2100, or X is bleen at t and t is during or after the year 2100. So in fact, if you take Grue and bleen as basic principles or part of your base properties in your language, then you can think of green as being a disjunctive property made up of those two properties. Whereas since our language, we take green and blue as being our basic color words, Grue and bleen are these weird disjunctive properties. And we can do the same thing for blue, of course. A certain thing X is said to be blue at time t if it's bleen at t and it's before the year 2100, and Grue at t, and t is during or after the year 2100. So whether we find change or not in a certain situation may depend on the language we use to describe the situation. If we're using the green-blue language versus the Grue-bleen language. Similarly, what regularities we find in a sequence of occurrences may depend on the language that is used to describe this sequence. And finally, we may find two regularities in a sequence of occurrences, one projectable and one unprojectable, such that the predictions that arise from projecting both are in fact in conflict. So here's a general claim. For any prediction whatsoever, we can find a regularity whose projective license that prediction. So let me illustrate with an example. Suppose that there's a small country that takes a census every 10 years. And it has taken 3 so far. So there have been 3 censuses taken so far. The population was 11 million at the first time, at the first census, 12 million at the second, and 13 million at the third. So if we were to plot this along the x-axis, so these are the years, 0, 10, 20, 30. The first census, there were 11 million people in this country. At the second, after 10 years later, there were 12 million people in this country. And the third census that was taken, there were 13 million. Now, one way you can note that I can draw a line to connect these 3 observations. So at the fourth census, at the next census at year 30, you can predict that there are going to be 14 million people in this country. However, so the inference that we're drawing is that all points representing the census so far taken have fallen on line A. The point representing the next census to be taken will also fall on line A. That's the inference we're drawing when we draw this blue line and we infer that at the next census, at year 30, there are going to be 14 million people in this country. However, here's the problem. The red line and the green line also fit this data. So the red line says you drop down a little bit, then you increase, and then you do a rapid drop. Similarly, the green line says you increase a little bit, decrease a little bit, and then you do a rapid increase. Both of these lines fit the data, and I can apply this inference here by replacing line A with, say, the red line or maybe the green line. So it's unclear what we should actually draw. Which one of these is the correct regularity to project into the future? Which of these lines is capturing the underlying phenomenon? So to summarize, in the Grue paradox, consider a gem expert. Now, this expert who speaks our ordinary language assumes nature to be uniform with respect to blueness or greenness of emeralds. And since observed emeralds had always been green, and since the expert is assuming that nature is uniform and the future would resemble the past in this respect, the expert predicted the emerald would remain green. However, consider the gem expert who speaks the Grue language. This expert will assume nature to be uniform with respect to the grueness or bleenness of emeralds. And since observed emeralds have always been Grue, and since the expert is assuming that nature is uniform and that the future would resemble the past in this respect, he predicted that the emerald would remain Grue. So the general point here, or the real problem here, is that it is self-contradictory to say that nature is uniform in all respects. It seems like we have to make a decision. Are we speaking the Grue language, or are we speaking the blue-green language, our ordinary language? And if so, if we choose between those two languages, we need to give a principled reason why we prefer one language over the other.